Yeah, I don't think I was recording before, but I am now. So that's that. Let's see what we can do to design a little counter of our own. We'll have a counter and counter. Here we go. So the counter does the following: 0, 1, 2, 3. We've seen this before. But now I put the input 0 on the arcs. The reason I did that is because I'd like to be able to change it. I want it to be able to go 3, 2, 1, 0, back to 3 if the input goes from 0 to 1. In other words, I want this to be an up-down counter. So now the question is, how do you do that? Well, this diagram is now the diagram of a finite state machine. And what you want to do is you want to get the present state and you want the next state, just like before. But the present state includes an input to show whether you're going up or down. And this will be up, and this will be down. So when u is equal to 0, we go 0, 1, 2, 3, back to 0. When u is equal to 1, we go 3, 2, 1, 0, back to 3. And so now I got to have the next state. And so if I'm in state 0, next state is going to be 1. I'm in state 1, and the next state is going to be 2. From 2 I go to 3, and from 3 I go back to 0. That's cool. But what if I'm in state 3? The next state is going to be 2, and it's going to be 1, and it's going to be 0, and after state 0, we go back to 3. This is a different sequence than that, you see. And so now, if you compare B plus to B, it looks like B inverted. And here, it still looks like B inverted. So now, if you want to make a D flip-flop input, you could. Okay. And if you want to do a T flip-flop, you could. So you could do a T flip-flop for A, and you could do a T flip-flop for B. And what you want to do is you want to see if it's changing. It looks like T sub B is changing on every single state. If you want it to change, you need to put in a 1. So now T sub B equals 1. Doesn't get easier than that. B. T sub B equals 1. But what about T sub A? If there's a change, then you've got to have a 1. Let's get a piece of paper or something here so we can see that. So over here you see A has not changed, so that's a 0. Here you see A is changing, so you get a 1. Here you see A is not changing, so you get a 0. Here you see A is changing, so you get a 1. That's easy. Here you see A is changing, so you get a 1. Here you see A is not changing, so you get a 0. Here you see A is changing, so you get a 1. Here you see A is not changing, so you get a 0. Does everybody kind of see that? Say I number my truth table. Now I can look at T sub A in terms of minimal sum of products if I like. What we'll do is we'll make a K-map. And now, I think maybe what we'll do is we'll fill in this K-map and write T sub A equals, and I think what we're going to have here is a 1 on row 1, 3, 4, 6, so it's 1, 3, 4, 6. Let's get a different color. And so this here, that's going to be, oh, we've got to label this K-map, right? So that's going to be U, B prime. And this here is going to be B, U prime B. So A is equal to U exclusive OR B. That's cool. That's cool. So now, yes, go ahead. This T sub A goes right in there because I want to know how to stimulate the input for the A flip-flop, the toggle flip-flop A, based on the present state, A and B, and the input U, because the input U is going to drive the circuit to count up or count down. See? So now I can write it out. T sub A is equal to U exclusive OR B, and now I can write out the whole circuit. Very simple circuit. So it's concept heavy, but drawing light, right? So here's T sub A and A prime, and we know T sub A is equal to U, if that's up or down, exclusive OR B, and here's exclusive OR, and then T sub B, it's B or B prime, is equal to 1. And there's my up-down circuit. And that's it. Your first up-down counter. Wasn't that fun? And the answer is yes, Professor Lyon, very fun. Well, look, you know, if you don't think it's fun, I feel sorry for you because it doesn't get any funner than this. This is it, man. This is as fun as it gets. This is fun. No, not fun? Okay, fine. Good, whatever. So that's that. You now have your first finite state machine with an up-down counter. I just think that's so much fun. That's so much fun. Let's do another one. I just had so much fun doing this. Let's do this. Remember the walking ring counter? The walking ring counter went 0, 0, 0, 0, 0, 1, 0, 1, 0, 1, 0, 0, and then back to the beginning. That was the walking ring counter. Just had the 1 sliding. So what we'll do is we'll give this is the state encoding, right? We'll just write 0 goes to 1, goes to 2, goes to 3. Is that right? No, that's not right. This is, what is this? This is 0, this is 1, this is 2, but that's 4. Ah, that's it. 4. How's that? So now I've got my little finite state machine. I can design, actually this is a counter. I can design this counter, right? So it's A, B, C. A plus, B plus, C plus. And now what? Oh, Let's encode this. 0, 1, 2, 3, 4, 5, 6, and 7. So if you're in state 0, next state is going to be 1. If you're in state 1, next state is going to be 2. That's all right. If you're in state 2, next state is going to be 4. If you're in state 3, we don't care. If you're in state 4, next state is going to be 0. State 5, we don't care. We're not doing that. We don't do 6, and we don't do 7. So now, let's get, oh, I forgot to do the D sub A, D sub B, D sub C. We'll just copy everything over. Because we chose a simple flip-flop for design using D flip-flops. And now, I got a 1 in row 2. I got zeros in rows 0, 1, and 4. All the rest are don't cares. I can loop this guy right there, and that's going to be B. That'll be equal to D sub A. And that kind of makes sense because B will fit right in through here, and that's a don't care, and these are all don't cares. So let's just set D sub A equal to B. In fact, if you think about it, you could make D sub B equal to C. Okay. And you can make D sub C equal to C. Now D sub B can't be equal to C. It must be equal to B. So that's cool. Now, for my walking ring counter, D sub A is equal to B, D sub B is equal to B, and D sub C is equal to C. And that's it. Pretty cool, right? So now you've got the walking ring counter under your belt. Who got confused by this? So we've got a homework we can look at. That would be homework number 11. No, homework 8. Sorry, homework 11. Homework number 8. Oh, sure. I opened the floor to midterm questions before, and nobody had any. Did you come in late? No, I said we got a midterm due. That's how I started the class. And I said going once, going twice, go on, and nobody had any questions. I said, great, you guys got the midterm nailed. So sure, yeah, we can do midterm questions, absolutely. Absolutely. Let's see if I can do that. close out the homework and open up the midterm. Now I'm going to scroll down to the number you're asking about. Bear with me a minute. Okay. This is question 24. You know what? Let's get a almost fresh piece of paper. And or is it XYZ? XYZ. And what else is in this thing? Oh, there's an enable. What else do we need to know? Oh, there's like an AND gate here. 3, 5, 6. Output is F. I think that captures number 24. 24. So, what's the question? Forget the question. A 3 to 8 decoder, right? So this is 3 to 8. Is connected as shown, where X, Y, and Z are inputs. Z is the least significant bit. What's the question? All right. Why don't we do the truth table on this one? Anybody know what the truth table is for this? Alright, you don't know that. How do you use De Morgan's theorem with an AND gate? Yeah, that's correct. So, that's 3, 5, and 6. Does everybody see that? Who got confused by this? So that's what I have for my truth table. Let's look and see what it says for my answer. F will be a 1 when all 3 inputs are 0. Here, all 3 inputs are 0. F is not a 1, so we know that's not true. The next one says 2 out of 3 inputs are 0. Well, this says 2 out of 3 inputs 0, and F is still not a 1. So that is not true. Then it says if no input is logical 0, the output will be a 1. Well, here, no input is logical 0. The output is still a 0, so that's not true. But then it says, if 1 out of the 3 inputs are a logical 0, F will be a 1. So that's true here, and that's true here, and that's true there. So basically, 1 out of 3 inputs is a logical 0 means 2 1s. So if there's 2 1s present, it outputs a 1, otherwise it outputs 0. And that's how you do that. But the key is finding the truth table. Did you have trouble finding the truth table? Anybody have trouble with that? Okay, well, that's good. Then any other questions about the midterm? The which is due today. So oh yeah, you can go. Sure. Okay. I need more paper. Just a minute, please. All right. What is the output for an 8 by 8 multiplier if the input is 1101 0010, and we're multiplying by 10111 0. No, I did it wrong. Shoot. I gotta start again. 1101 0010 100 111 00. I think I did it right this time. So I want to multiply this number by that number. Multiply. How's that? Does that look right? I think I did it right. So 0 times all of this is 0. 0 times all of this is 0. 1 times all of this is itself. 1 times all of this is itself. 1 times all of this is itself. 0 times all of this is 0. 0 times all of this is 0. 1 times all of this is itself. And the nice thing about multiplication tables in binary is they're little. 0 times 0 is 0, 0 times 1 is 0, 0 times 1 is 0, and 1 times 1 is 1. Those are my multiplication tables in binary. Right? So now all I have to do is addition. 0 plus 0 is 0, 0 plus 0 is 0, 0 plus 0 is 0, 1 plus 0 is 1, 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 1 plus 0 is 1. This is fun. 1 plus 1 is equal to 1 carry the 0. No. 0 carry the 1. Plus 1 is 1 carry the 1. So now I have another 1 plus 1 plus 1, which is 1 carry the 1. 1 carry the 1. 1 carry the 1. 1, 1, 1. How many 1s is that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That's 12 1s. So if you put a leading 0 in there, you can find the answer. And that's that. What do you think of my solution? Is that sure? Yeah. Is anybody confused by this? Multiplication and binary. All you need is to and shift. That's it. And in shift. And add. Any other questions about this midterm? This is your very last chance to ask questions. 32. Compute 7 minus 1. Okay, 7 minus 1 equals 6. There, I did it. Wait, using 2's complement. Oh, well, let's see. 7 is equal to 1, 1, 1, but I need a leading 0 if it says assume there's only 4 bits available to represent the numbers. Now, 0, well, let's start with 1, is equal to 0, 0, 0, 1, base 2, using 4 bits. And now I want to form minus 1. So I complement and I increment, and what I get is 1, 1, 0, whoops, 1, 1, 1, 0, right? Plus 1, which equals 1, 1, 1, 1, base 2, so that's minus 1, using 2's complement. It's minus 1 base 10 using 2's complement. So now, 7 plus minus 1 is going to be 1 plus 1, which is 0, carry the 1, 1, carry the 1, 1, carry the 1, 0, carry a 1, which falls on the floor. So at the end of the day, you have 0, 1, 1, 0, base 2 equals 6. That is the 2's complement representation of 6, base 10. Who got confused by that? Anybody? Any other questions about the midterm? Sorry, 57? Okay. 57. What is the binary representation of the following negative number in 2's complement? Okay, so he says 1, 1, 0, 1, base 2. We know it's a negative number because it's got a 1 in the most significant bit. So to turn it into a positive number, I do the same thing as I do as turning a positive number into a negative number. I complement and then increment. And so now I get 0, 0, 1, 0 plus 1, which is equal to 0, 0, 1, 1, and that is base 2. And it is the number 3. So this number is the 2's complement representation of minus 3. And that is because the 2's complement of this negative number is 3. How's that grab you? Anybody got any questions about that one? Any other questions about this midterm? Going once. Going twice. Oh, wow. There's more. Okay. 59. Convert the following decimal number to... I'm going to read it again. Convert the following decimal number to binary using 6-bit 2's complement representation. decimal number is 13. And we want binary. And he wants it to be 6-bit. 1, 2, 3, 4, 5, 6. There it is. That's a positive number. This is a positive number. Now, if you wanted it negative, then you'd say that's not what he asked. Just wanted a 2's complement representation of positive 13 base 10. That's this, using 6 bits, padded with 2 bits. What do you think? Any questions about this one? That was question 59, by the way. No questions? How about more questions about the midterm? Going once? Going twice? Going 3 times? Okay, I declare the midterm coverage is finished. Okay, I'm closing the midterm. Here I am closing the midterm. The midterm is closed. And that's that. Let's go back to homework number 8 so we can see if there's any questions about that material. So you guys are all set with the midterm now. That's it. We're done. That's cool. That's cool. Okay. So in our last exciting class, we were looking at some characteristic equations, and we saw that for the D flip-flop, the next state, Q plus, is equal to D, to the input. For the RS flip-flop, the next state, Q plus, is equal to S or R prime Q. How can that be? How do we know this? How does that work? Well, let's have a look. Suppose what's Q? Well, Q is equal to Q prime and S inverted. And what's Q prime? Q prime is equal to Q and R inverted. Does that look about right? So here comes R. It's being ANDed with Q, and it's an AND gate, so it's inverted. So then, what happens in the next state? Q plus. Well, Q prime, we know what that is. It's Q R prime times S quantity inverted. Okay. Well, I can use De Morgan's theorem on that, and so that becomes S prime or QR. So that's cool. So that's if you take Q prime and back substitute it in here. So that's one way to write the present state next state equation. But suppose you went the other way. Suppose you took this Q and you put it in there for the next state. Equals, and now you could say it's Q, which is Q prime S, inverted, ANDed with R, quantity primed. So now what do we got? Well, De Morgan's theorem again. So now I got Q prime S or R prime. So that's kind of cool. So this kind of looks like that, but there's a difference, right? What if what we did was we wrote it wrong? What if we wrote R and S over in here? Then what would happen? Then Q must be equal to, let's see now, that's going to be Q prime R. And then Q prime is going to be equal to SQ. And now Q plus is going to be equal to SQ Q plus, we're going to use let's see, we'll do it again. Q prime, Q plus, is going to be equal to Q prime, which is SQ, R. That's interesting. Let's go the other way with that one. That's cool, actually. I didn't realize that would happen. Q plus could be equal to S times Q prime R. Yeah, so neither of those seems to work out. So you can get sort of the same thing over in here with a slight difference. The S prime here has been inverted and the R has not. So you can kind of get the present state next state there. It's not exact. I'm not sure why, because I've done this before and it came out exactly right. And in fact, there's a video of this working on the web, and I was looking at it and I said, yeah, that looks easy. Then when I tried to reproduce it, it came out a little backwards. Not sure why. Small variation there. But you can kind of see how those things will work out. You can get present state, next state equations. Moreover, if you look at JK, your next state is going to be JQ prime or K prime Q. And if you look at T, it's the same thing as holding J and K identical. It's going to be T Q prime or T prime Q. So if you set J and K equal to each other and call it T, then you've got a toggle flip-flop. And so you do that just by doing this. And that makes your toggle flip-flop happen. So that's cool. Let's look at some questions out of homework number 8. So here's one, and we did this before. If you have JK with an inverter going through, that makes this into a T flip-flop. And if you wanted to, you could write this in any one of a few different ways, one of which might be as a latch, SR latch, feeding a couple of NAND gates. Whose output is in clock, going into another set of SR inputs. So this is the master-slave relationship again. And now what you can do is you can gate the inputs here. Run it into your clock. And then take S and R. And now you've got your D input. So now you've got your master-slave clocked D flip-flop. So that would be number 1. So what they're trying to do with that one is you're trying to do a match. So that's a master-slave D flip-flop. Looks like there's a small bug in here, and it's in the answer key. Let me see if I can edit that. It'll let me. This is the first thing is a master-slave RS latch. It says master-slave RS latch, or flip-flop if you like. Okay. Looks like we have 17 people already have submitted, which is cool actually. Are there any questions about homework 8? No questions. So we did a bunch of flip-flop conversions. I'm going through this now just to see if there's any other questions we should try and address. Oh, and the read switch. That's one we should look at. So a read switch uses a magnet to close the switch, but the magnet doesn't have to be in contact with the switch. So what you do is you fill up a glass envelope with an inert gas, and then you bring a magnet in close proximity to the north and south poles. It'll get the switch to close, and that works in a let's say an explosive environment. Or you can use it to make like a burglar alarm. When somebody opens the window, the switch closes, and then the window opened to sense it, and somebody can make the burglar alarm go off. And then you can, I don't know, call the police, or have the machine call the police. It's even better. Any questions about homework 8? No questions? Really? Well, suppose we take a look at homework number 9 then. Oh, I just closed it, homework 8. That's alright, just a minute. I'll open it again. Edit the test. Homework number 8, problem number 5. So we actually did that, right? Because that's what this is. What did we do? We made a D flip-flop using a JK flip-flop. Right? You can tell it's a D flip-flop, right? Because it's got a D going in. You can tell we're using a JK flip-flop because this says JK on it. So we made D using JK. You know, this is another one, right? Here's JK. Here's J. Here's K. Being wired together. Okay, I used JK. What did I make? What is this flip-flop? Well, let's assume that Q is equal to Q plus is equal to J Q prime or K prime Q. Now let's let J equal K, because you wired them together. So now I'll set it equal to X. So the Q plus is equal to X Q prime or X prime Q, because I put X in there for the both. So what is this the characteristic equation of? Alvin, can you go ahead? That's a T. Yeah, so that would be a T Q prime or T prime Q. So what we did was we made a T flip-flop using a JK flip-flop. So that's what that did. Right, so this is the D right in here. That's a T. They both have one input, but you can see they're different, right? Let's look at it a different way. Suppose we start with the characteristic equation and we let K equal J prime, right? Because we've got an inverter up here. So if K equals J prime, then Q plus must equal J Q prime or J prime prime Q. Well, what's J prime prime? J Q prime or J Q. So now I can factor it out. J times Q prime or Q. What's Q prime or Q? Well, that's 1. Right, because that's like 1 or 0. 1 or 0 is equal to 1. So whatever the input is, it's J. So if Q plus equals J, that's the same as Q plus equals D. Right? So that's saying Q plus will be whatever we use for input. That's why we call it a D flip-flop. And you can get that directly from the characteristic equation through Boolean algebraic manipulation. Does it make sense to people? Are we... Yeah, who's confused? Well, that's all the time we have for today. It's a beautiful day out, although it's a little windy and cold. So stay warm, stay safe, and thank you very much for your attentions. Thank you.